Hello everyone, I'm Hanjun Hee. In this video, we'll design AI based on Mover and create a simple feature that changes movement mode depending on the situation. We'll only use the Mani template, so I'll start with the default third-person template. First, I'll enable the Mover plugin. I'll restart later. Next, I'll create a pawn class that will use Mover. The character class already has CMC, so to use Mover, we need to create it as a pawn. I'll create it in a dedicated folder. Once the IDE has finished loading, first I'll add the module to build.es. Now, let's continue defining the pawn. We'll need a capsule and a mesh by default, so let's create them. Next, I'll create Mover and a nav component dedicated to Mover. Also, to use Mover, we need iMover input producer interface. I'll implement the interface. Initialize the components in the constructor. Now we'll implement produce input. Unlike CMC, Mover receives the player's input values directly. The reason it's designed this way is to predict network movement based on input. Of course, network prediction, one of Mover's strengths, doesn't provide a major benefit for AI that only moves on the server. However, if you're considering a Mover-based design in the long term, integrating even the AI with Mover will be better for logic reuse and maintainability. Next, we'll implement the input. Since AI can't provide input directly, we'll pass the navigation movement value as input. For the directional intent, we'll make it face the current input direction. Now that everything is implemented, I'll build and restart the editor. After restarting, let's create a BP from MoverAIPawn. The first thing we need to do is set replicate movement to false. As I mentioned earlier, the reason is that Mover handles network prediction. If a player is sprinting locally and then stops, we need to roll back the prediction correction that made them appear to keep sprinting from another player's perspective. This feature can conflict with replicate movement, so it needs to be disabled. Next, let's set up the mesh. We'll also assign the ABP, let's call AI MoveTo from begin play. Now place the AIPawn in the map. Then place the NavMesh in the level as well. Press P to check that the navigation area has been generated correctly. Let's move the AIPawn up into the air so it doesn't interfere with navigation. Let's test it right away. It moves fine, but there seems to be an issue with the ABP. The reason is that the ABP is referencing the CMC. For this, we'll duplicate the existing ABP and make one specifically for Mover. Right now, it's referencing character and CMC. We'll change these to pawn and mover. Change the other parts to use the mover approach as well. Mover doesn't have acceleration, so here we'll simply use velocity. In this example, the AI won't use strafe. Switch it to the ABP we just modified. If we test again, we can see that the animation works properly. Next, Mover has a movement mode. The character mover we're using has walking, flying, and falling modes by default. Here, we'll implement it so the AI can dynamically use the appropriate movement mode. First, in walking mode, we'll create a simple feature for stepping over obstacles. To do that, block the AIPawn with a suitable wall. Normally, you need a NavLink to get over a wall. We'll make Recast NavMesh generate NavLinks automatically. Just enable Generate NavLinks. You can also decide how NavLinks will be generated. I'll set up 2 rules, using values I found to work reasonably well. You can define these values based on your own requirements. We've created the NavLink like this, but it probably won't work yet. That's because we haven't defined what the AI should do when it reaches the NavLink. To do that, we need to override generated NavLinks proxy. I'll create a class for this. I'll save this in the AI folder as well. Here, we'll detect the obstacle between the NavLinks and create traversal data. Then we'll use that data when moving over the obstacle. First, I'll create the traversal data struct. Next, I'll define the configuration properties. First, we'll define the maximum height of the obstacle. For this, we'll use the same value as the jump height used when creating the NavLink rules. Next is the interval used to check the depth of the obstacle. Lastly, we'll define the minimum height required to be considered an obstacle. Now I'll define the required methods. Generated NavLinks proxy has a callback that is triggered when the AI reaches a NavLink. We'll call DoTraverse from that callback. To do that, we'll bind it, but make sure it is not called on the CDO. Next, we'll override getWorld. The reason we're doing this is, as of Unreal 5.7, generated NavLinks proxy's getWorld causes a crash. Finally, let's implement DoTraverse. Here, we'll use a line trace from the current location to the target location to detect obstacles. To do that, we'll get the distance between the current location and the target location. First, we'll get the current foot height. Now we'll perform line traces step by step toward the target point. Let's define the variables we need for this. Scan-high-z is the highest height to use as the start point. Scan-lows is a height lower than the foot, used as the end point. Top-z threshold means any height below this value will not be treated as an obstacle. Num_steps determines how many line traces to run at evenly spaced intervals. Now let's perform the line trace. If this is the first point we reach, it's the front of the obstacle, so we can treat it as front ledge. Also, whenever we detect an obstacle, we'll update last top hit. And if it is no longer an obstacle, we've passed back ledge, so we break. Also, if the loop didn't find front ledge, then it isn't valid. Now let's create traversal data. We'll have the AIPawn use this. So let's create a method in AIPawn. I'll call it directly from here. Now I'll close the editor and build it. Once the build is complete, I'll import a few example animations. These are all the animations from the Gaspi project retargeted to the mannequin. I'll put the link in the video description. Extract the archive, then launch the editor. If you go into the animation folder, you'll see all the animations like this. I'll only use the traversal animations here. There are 4 animations to import in total. I'll make all of the animations use root motion. Now create animontages for all of them. I'll adjust the start and end times so the AI can use them more easily. These are just values I found that work well, so adjust them however you like. Next, we'll use motion warping. We'll use the front ledge and back floor from the traversal data we got earlier. Set the range up to the point where it reaches front ledge. Set the name to front ledge. Here, we'll use the Z-axis and set the curve to linear. Next, create motion warping for back floor as well. For this, just set it up to the target position. Now name it back floor. The rest is the same, but when moving toward back floor, we won't use rotation. Lastly, Animontage has blend in and blend out by default. Setting blend out to 0.05 felt natural to me, so I'll use that. Now I'll apply the same setup to the remaining animations. Everything is the same, except for setting the sequence and motion warping sections. Next, we'll create a ChooserTable so it selects an anim montage based on traversal data. First, set the return value to anim montage. We'll also take traversal data as an input. Now I'll add 4 anim montages to the rows. The columns will be the branch conditions used to select a row. We'll use the depth and height from traversal data. Select float range. I'll apply the range values the same way as in the GASP example. Now that the ChooserTable setup is done, let's implement DoTraverseLogic in AIPawn. Here we'll run play montage. Use the ChooserTable we just created. This will output an anim montage that matches the conditions. However, traversal data that doesn't match any branch condition may be passed in. In that case, the anim montage will not be valid. So we'll run a validity check. Next, add a MotionWarping component. Before running play montage, we'll set front ledge and back floor. Also, for a more natural result, we'll disable collision while the anim montage is playing. Now we'll run play montage, but Mover needs to use its dedicated function. A regular function, or the function provided by GAS, will still run, but root motion will not work. Now that the BP implementation is complete, we'll register the link proxy class. This way, when the AI reaches the NavLink, it will call DoTraverseLogic. Now let's test it. You can see that it climbs over a suitable wall properly using root motion. Let's adjust the obstacle and see if the other anim montage is selected correctly as well. As you can see, depending on the placement, a NavLink may not be generated. As you can see, motion warping is not perfect. In the GASP sample, this is corrected with an attach bone. But that's based on UEFN, so it can't be applied directly to the mannequin. We won't cover that work here, but if you need fine adjustments for motion warping, I recommend looking up the related topics. Volt also works properly depending on the situation. Next, we'll implement the movement mode example. For AI flying pathfinding, we need a separate plugin. I'll use this one, and I'll put the link in the video description as well. I'll close the editor to install the plugin. After extracting it, we'll put this folder into the plugins folder. If you don't have a plugins folder, you can create one. Since we need to use it in C++, I'll add the dependency to builder.cs. Rider doesn't recognize the plugin yet, so I'll make sure the plugins folder is included in the solution. I'll also run refresh solution. Now that the SVO plugin is recognized properly, let's continue. By default, we move in walking mode, but we'll create a feature that moves in flying mode when needed. To do that, we'll create a custom movement method. We'll also create a movement completed delegate. I'll create a method to receive the existing move to callback. We'll define a temporary field to store the delegate. We'll also create a field to store the flying path. Now let's implement the custom movement method. First, initialize everything. Next is validation. Now here we'll check whether the navigation path is valid. If it's valid, we'll use walking mode. If not, we'll use flying mode. Here, is partial means whether the returned path is only partial. I only want to use walking mode when we can reach the target location. So I won't accept partial paths for walking mode. Also, if the path is valid, we'll run MoveTo and register the delegate as well. If we reach this point, it means navigation is not valid. So we'll perform pathfinding for flying mode, and if it succeeds, switch to flying mode. If it fails, do nothing. Now that everything is implemented, I'll make the existing move to call the delegate. Now we need to call the delegate and then clear it. But if we just proceed like this, issues can occur. Inside the delegate, MoveTo may be called again. Then the new MoveTo will overwrite the existing temporary delegate field. Normally that would be fine, but it can cause problems while the delegate is executing. So it's safer to copy it into a local variable and execute that. Now that the implementation is done, next I'll modify produce input. Now here, we'll branch the input based on movement mode. If it is in flying mode, it should have received a valid aerial path. It will move through each path direction in sequence. We'll keep applying input toward one path point, and when it gets close, make it head toward the next one. Also, when pathfinding is complete, we'll switch it back to walking mode. The existing navigation method will only be used in walking mode. Now let's build it and run the editor. Once the editor is open, we'll switch it straight to the MoveTo we created. Next, we'll configure the settings for the Flying Pathfinding plugin. We'll add a dedicated collision channel. Set the default to ignore. Then make sure all terrain placed in the level is blocked. Next, we'll place a volume in the level for flying pathfinding. Now we'll raise the wall so it can't be crossed in walking mode. Let's test it right away. The SVO volume resolution seems too low, so let's increase it to 7. Now you can see it moves in flying mode, and when it reaches the target, it switches back to walking mode. Let's check whether the custom MoveTo also works properly with the existing functionality. It reaches the target without any issues, and the arrival callback is called correctly. Next, let's also check the callback for unreachable targets. If it works correctly, it returns true. If it's not possible, return false immediately. Also, let's look at the case where the ChooserTable fails. It returns the chooser failure log and false. You can add branches to the ChooserTable based on your requirements. That's it for this video. Thank you for following along with this long video, and thank you for watching.